Okay, so in the previous lectures I talked about propagation of light in a homogeneous transparent medium. If the light travels in a medium which is not homogeneous, or it encounters a surface separating two different homogeneous media, then what we call it refracts at the surface. If the incidence is oblique, it bends and all that. So let us do an experiment and see what refraction is. I have this bottle, and in the bottle I have taken some water, and above the surface of water we have air. We have put some smoke here in the air and some suspension material in this water to give scattering centers. A light beam is incident on this water surface going from air, it falls on the water surface, and you can see it splits in two parts. One part is reflected back in air and the other part goes inside water, which we called refraction or refracted beam. So you have an incident beam, you have a refracted beam, and you have a reflected beam too. With each refraction, most of the time you will see that there is some reflection also. If you call them rays, you can see that if you think of a normal to this horizontal water surface at the point of incidence, a vertical normal, then the incident ray, the reflected ray, the refracted ray and the normal, they are all in one single plane. So you do not have to really specify first law of reflection separately and first law of refraction separately, because refraction will be most of the time it will be accompanied by a reflection, and all four are in one single plane. Now with the normal, with that vertical normal in this case, the angle between the incident ray and the normal is called angle of incidence. We denote it by I, and I am focusing on refraction. The angle between this refracted ray and the normal is known as angle of refraction, and we will call it R. So I is the angle of incidence and R is the angle of refraction, and it turns out that sine of I, the trigonometrical function sine, sin sine of this angle I divided by sine of this angle R is equal to speed of light in this first medium, which is air here, divided by speed of light in the second medium, which is water here. So I will say sine I by sine R is equal to V1 divided by V2. Now you can see that the light, when it is entering water, it bends towards that normal. So the angle of incidence is more and the angle of refraction is less, I is more and R is less. So sine I is more, sine R is less, and therefore sine I by sine R is more than 1. What does that mean? V1 by V2, speed of light here in the first medium divided by speed of light here in the second medium, V1 by V2 is greater than 1. Speed of light is more in air and speed of light is less in water. Now in this situation, light is going from the water, falling on the surface, and part of it is getting refracted in air. So you can see a beam coming out in air, that is refraction, and a part is also reflecting. Focus on the refracted beam and just think of a normal here at the water surface, and you can see that the light is bending away from the normal. So the angle of incidence, which is the angle between incident beam and the normal, it is smaller, and the angle of refraction is larger. Now, in this situation, light is going from the water side and falling at the surface, and you see the whole light is reflecting, nothing is coming out in air. This is called total internal reflection, because the whole of the light is reflected in the same medium and nothing comes out. That depends on the angle. If this angle of incidence is larger than some critical angle, then this kind of phenomena will take place, else you will have what you saw earlier. The fact that light refracts when it changes medium has many interesting results. One of the very widely used observation, which is used as a starting point in most of the textbooks, is a pencil half dipped in water and half in air, placed in some tumbler or something. Now, if you do this experiment in a transparent cubical box, say made of glass, you will have fantastic views of this pencil if you go from one side to the other side, from top, from side, from corner. Varieties of things you will observe from there, and analyzing these observations is a very good exercise to practice refraction. This is the top view. Seeing from above the water surface, the pencil looks as if it is bent at the surface of the water. This is one view. We are seeing from some corner. This is another view. It seems that at the surface there are two pencils, two images at some angle, as if pencil is splitting in two parts. You do this experiment and see this pencil from various angles and enjoy the different types of patterns that it makes. This is another beautiful experiment. We call it mirage in a bottle. You can see we have a box or bottle, and we have some liquid here, and in this liquid light is falling from outside, and it enters the liquid, and then you can see it goes in a curved path. It enters almost horizontally, or it enters at some angle and gradually it bends, somewhere it becomes horizontal, and after that it goes further down. In the pictures of mirage that are given in textbooks, you must have seen that light bends downwards, and then at some lower level it becomes horizontal and then goes up. It is inverse of that. Here light is going upward at the entry, and then it becomes horizontal at some high point and then goes down. What we have done here? What is this liquid? This liquid is essentially salt solution up to some height, and on top of that we have normal water, and there is a gradient of concentration of that salt because of diffusion at the surface. That gradient comes out. So, the refractive index or V1 by V2, the speed of light, it gradually changes. This concentration at the lower end is more, so the speed of light is smaller, and here at the boundary where the diffusion has taken place and there is a concentration gradient, the velocity is gradually increasing as you go up, and of course finally there is air, but the light does not come out in air. If the surface separating two homogeneous transparent media is curved, like a spherical surface or a cylindrical surface, the same rules of refraction will work. you have to draw a tangent plane at the point of incidence, and then you draw the normal, and the same sin I by sin r equal to V1 by V2 will work. And this helps us in making varieties of optical instruments like telescopes, like microscopes, lenses themselves, the spectacles that we wear when we have problem in seeing. All these take advantage of this simple rule of refraction, sin I by sin r equal to V1 by V2. One of the very simple demonstration of refraction at curved surfaces is here. Look at this glass tumbler. It is filled with water, and then I have a printed sheet of paper, and you see the size of the letters which are here, and then I am just putting it behind this glass tumbler so that the printed letters are seen through the water. Light from those printed letters are going from air to water and then coming back to and falling in the camera or in your eyes, and you can see the size of letters that has increased very significantly. So all these kinds of effects are coming from refraction at curved surfaces. So here is another wonderful experiment, colorful also. You can see I have a lens here, convex lens, also popularly called magnifying lens, and I have put some opaque disc here at the center, so that rays will only go through the outer part of this lens, and then I have a bulb here, a torch bulb which is glowing, and then light from this bulb goes through this lens and forms an image on the screen. Now I will be showing you the image here in somewhat darker environment so that you can see the image, and we will just change the position of the lens and you will see how the image changes. Okay, you are seeing the image. The image is in the form of a ring. The outer periphery of ring you can see, it is reddish, and the inner periphery is bluish. You remember the center we have blocked. The light is going only from this annular part of the lens. So center is blocked. So center is dark, that is perfect. But then the rays which are going from the lens, the annular part of the lens, they are split in different colors. From the source, it is a monocolor thing. It is somewhat yellowish white light that is coming, but it is a monocolor. And after going through this lens, it is splitting in different colors. And you can see that violet is or blue is bending more, so that it is on the inner side of this ring, and red is bending less, that is on the outer side. Yellow you can see somewhere in between. Now let me change the position of the lens and take it towards the screen, and you see the image how it changes. So I am taking this lens towards the screen. You can see more sharp focusing. This blue component is almost focused. You can see a small dot at the center, a very small dot at the center. Red is still yet to focus, and I am taking it further towards the screen, and now you see what happens. Now you see what happens. What do you see here? You can see that the center is dark, very sharp dark, and then you have red, and then the blue is on outer side. Okay, look at here, look at here. your center is dark, and then you have that reddish, and then yellowish, and blue is outside. It changes the order. It changes the order. If the lens is here, then red is outside, blue is inside. If lens is here, then red is inside and blue outside. So, you do it yourself and enjoy this colorful experiment. So, what do we learn from this experiment? First is the white light, what we call white light, has different colors, and in terms of waves, different colors means different wavelengths. Red will have largest wavelength and blue violet will have smallest wavelength in that visible range. So, when it passes through the glass, when it changes the medium, then light bends because the speeds are different, refractive index is different. And for different wavelengths or different colors, this refractive index or speed of light is different, and therefore they bend by different amounts, and then in the transmitted side, on the other side of the lens, the colors are separated. Violet bends more. What does that mean? It bends more means refractive index is more. It goes slower than the red, and therefore violet focuses earlier and red focuses later. And if you put the screen closer to the lens, the distance between lens and the screen is less than those focal things, then you see this bluish thing inside and the red things outside, because blue will be focusing earlier and red will be focusing later. But if the separation between this lens and the screen is large, then already that focus thing has taken place, blue has focused earlier, and therefore the cone which is diverging from blue is wider than the cone that is diverging from red, because red is little ahead of that, and hence what you see is the reverse, blue outside and red inside. So, from this we know that for blue the refractive index is more as compared for that with red, and therefore the speed is slower for blue in glass than the speed of red. So, our next experiment is on prism. You must be familiar with the prism. Here is that prism. It is made of glass, and there are 3 rectangular surfaces, here 1, here 2 and here 3. We will be using this rectangular surface and this rectangular surface. So, I have a laser, a light source, light starts from this torch, falls on one surface, this rectangular surface here, and enters from air to this glass, goes in the glass and then reaches this other rectangular surface, and it comes out from here and then it will fall on this. At this moment light is not falling on the prism, and therefore it is just going straight and falling on the screen here. So, let me remove the prism further, and you can see that the light is straight going from this torch and is reaching here. So, this is the straight path. Now, let me bring this prism in the path of this light. And now it has gone through the prism, first refraction here, second refraction here, and the spot comes here. So, the light which was going straight and falling here, now it is deviated, it has turned because of the 2 refractions, and now it is reaching here. You can measure this angle of deviation. What is that? The final rays is going in this direction and falling here. The initial ray, when the prism was not there, was going straight and falling somewhere here. So, this angle between this initial direction and this final direction, that angle is angle of deviation. Can I reduce this by turning the prism? If I reduce this, this spot should go towards the original direction. So let me turn this prism and try to reduce the angle of deviation. Am I able to do that? I am increasing the angle. The angle of deviation is increasing. It is deviating more and more away from the original direction. So let me turn it in the opposite direction. Yes, now it is going towards the initial direction. So I am rotating it as seen from top anti-clockwise. Anti-clockwise, more anti-clockwise, more anti-clockwise, more anti-clockwise, more anti-clockwise, more anti-clockwise, more anti-clockwise. It has gone away. Now let me rotate it clockwise. So I am rotating it clockwise now. So clockwise, 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 clockwise. It's going towards the straight path, and that's it. Once again it goes away. So I cannot bring it any more closer to the straight path. This is the minimum deviation which will always be there. I can increase the deviation by rotating this prism, but I cannot decrease the deviations. This is minimum deviation. Do you have a prism in your house? Not of this type, maybe not of this type, but it's very likely that you do have a similar thing which can act as prism. And what is that? That is a normal plastic scale. This is scale. Now if you look at this scale, in the middle you have flat parallel surfaces, but if you look at the edges, there is some tapering. The back side is, the whole thing is flat. On the back side, whole thing is flat, but on the front side, middle portion is parallel to that back surface, but near the end it is tapered. So if you just consider this part near the edge, you have two surfaces, one surface and the other surface, and they are at some angle. And if there are two surfaces at some angle, and in between those two surfaces you have a homogeneous transparent material, that is a prism. So this should be a prism. Let us see if it does all those activities which the prism had done. So straight path, the light is going and falling on the screen here, and now I am bringing my scale prism in the path of the light. So here it is. This was the straight path, and now it is going through my scale prism, and you see that it has deviated. It has come from somewhere here to here. So it's doing what? So can I decrease the deviation? Let me try. I'll give a anti-clockwise rotation to the prism. What is happening? It's increasing. Deviation is increasing. So give a clockwise rotation. Clockwise rotation. It has decreased. It has decreased. I am giving clockwise rotation. It has decreased. No more. No more. I am giving rotation, but it is not going further closer to the original thing, and now the deviation is increasing. So this is the minimum deviation. So the plastic scale in the drawing box is a very good prism, and if you can measure this angle of minimum deviation, you can calculate refractive index of this plastic material.